All right, everybody. Today we're going to cover the last new material for this chapter, and the idea we're going to be talking about today is called L'Hopital's rule. And this is going to help us find derivatives of functions that we weren't able to find before. So first, before we talk about L'Hopital's rule, we're going to review what we know so far about evaluating limits. And so we always said the first thing that we're going to try to do when we evaluate a limit is we're going to try to plug in the number. Okay, and if it works, we're set. We're done with that problem. So for example, let's say I had the limit as x approaches 5, of x squared minus 1. We would plug in 5 squared, or 5 for x, so we'd get 5 squared minus 1, and our limit would be 24, and we're done. Obviously, that's a simple case, but the idea here is to try plugging it in, and if it works, we're done. But we know there's times when plugging it in is not going to work. So we had 3 algebraic methods that we could use to try to simplify the problem before plugging in. The first was factoring. The second was finding a common denominator. And the last one was multiplying by a conjugate. And we found that took care of most cases. However, we did have some other special cases. In number 3, it says sometimes limits approach positive or negative infinity. And so I actually want to scratch this part off here and focus on the second part. Okay, when limits are approaching positive or negative infinity, remember that's typically because we have a vertical asymptote. Right, so there's something going on with my function. So let's say I have a vertical asymptote here, and as I approach that value, that asymptote is making my my behavior either go to positive infinity or negative infinity. So when I'm thinking of limits approaching positive or negative infinity, I'm thinking there's a vertical asymptote. Okay, then other times we looked at limits as x approaches positive or negative infinity. Excuse me. And in this case, we're thinking horizontal asymptotes. So for example, let's say we are taking the limit as x approaches infinity of 3x squared minus 5x plus 2 over x minus 7. Right, and we said here, if we're looking at positive infinity, we're just worried about that end behavior. We said what we only really cared about was the highest power in the numerator and the denominator. And so we said if we simplified that, this end behavior is really the same as the limit as x approaches infinity of 3x. And obviously, as x gets larger and larger, that limit is going to go to infinity. So we treated that just like we did when we were considering horizontal asymptotes in pre-calc. So up until now, that has taken care of all the limits we've needed to evaluate. However, if we look at something like here, limit as x approaches 0 of sine x over x, we realize pretty quickly that we still don't have a way of coming up with that limit. So there's no algebraic method that I can use to simplify it, and if I plug in, I'm going to get 0 over 0. So this is where derivatives help us out with limits, and this is where L'Hopital's rule comes in. All right, so this is our new strategy for handling some of these limits that we haven't been able to deal with so far. So if you're trying to plug in your number to a limit and you get either 0 over 0 or infinity over infinity, we call these indeterminate forms. And if that's the case, we can use this new rule called L'Hopital's rule. And what that rule says is we can take the derivative of the top and we can take the derivative of the bottom, And then we can try evaluating that limit again. And we can do this process over and over again until it works. The key idea here, and I'm going to make this note here, we can only use this if we have an indeterminate form. So only if I try to plug in and I get 0 over 0 or infinity over infinity. So the first thing we always need to do is try plugging it in and see how it comes out. So let's look at this example. If I were to plug in 0, sine of 0 would give me 0. And obviously if I substitute 0 for x, I get 0 over 0. That is one of my indeterminate forms. So that says that I'm okay to go ahead and use L'Hopital's rule. And what that tells me is that this limit is equal to the limit as x approaches 0. And the rule tells me I differentiate the top, which is cosine x, and I differentiate the bottom, which is 1. So obviously simplifying it here, I get the limit as x approaches 0 of cosine of x. So now I try plugging in. If I plug in 0 into cosine of 0, I just get 1, so my limit is 1. So now we have a way for calculating that limit. So we're just going to go through 4 more examples here to make sure we understand how the rule works and when we can use it. All right, I take that back. We only need to go through 3 because we just did this example. Great, moving on. Number 2. Now I actually want to spend a minute talking about number 2 because we actually had a way of dealing with this before now. And I just want to go over that and show why L'Hopital's rule comes in so handy. So back in chapter 2, I guess, here's how we handled this before. This was our old way of doing it. We said here we could take this, if we plugged in 0, we would get 0 over 0. So obviously we knew we had to do something algebraically with this function. So we said we knew we could multiply by the conjugate. So I had 1 times, or the square root of 1 plus x minus 1. And we multiplied top and bottom by the square root of 1 plus x plus 1. Okay, and then we went through and did all our algebra magic. So when I FOILed the top, I ended up getting 1 plus x minus 1 all over the x times the square root of 1 plus x plus 1. And if I simplified my numerator, I got x. In the bottom, I still had everything down here in the denominator. And then I could cancel an x. So this came out to be 1 over the square root of 1 plus x plus 1. So now we realized if we plugged in 0, we didn't have a problem anymore. So we said that this limit was equal to the limit as x approaches 0 of 1 over the square root of 1 plus x plus 1. And if we plugged in 0, we got 1 over 2. So that works out just fine, and it'll still work, but let's take a look at how we can do this the new way. So I'm going to take my same limit, which is the limit as x approaches 0 of the square root of 1 plus x minus 1 over x. And so now I always need to check if I have one of my indeterminate forms. So if I plug in 0, I'm going to get 1 minus 1, which is 0. On the denominator, I have 0, and that tells me I can go ahead with L'Hopital's rule. So remember, what L'Hopital's rule says is that I can take the derivative of my numerator. So I have 1/2 times 1 plus x to the negative 1/2. My minus 1 term drops out. That derivative is just 0. Then I could take the derivative of my denominator, and that's just 1. So if I just rearrange some things, rewrite this, I get the limit as x approaches 0, of 1 over 2 times the square root of 1 plus x. So now I've differentiated once, so I'm going to go ahead and try plugging in now. So on the top, I'll have 1, and on the bottom, I get 2. So actually, with considerably less work, I've arrived at the same limit. So that's one of the benefits of using L'Hopital's rule. All right, let's look at the next one. So remember, the first thing we're going to do here is we're always trying to identify what the indeterminate form is. And so I think here it's worth really quickly looking at the graphs of secant and tangent to see what's happening as I approach pi over 2. So let's first look at, I'm going to kind of try to section this off here so our work doesn't run together. Let's look at the graph of secant x, which we know is 1 over cosine x. And I know cosine is going to be undefined at pi over 2, so I'm going to have vertical asymptotes. So if this is pi over 2, I'm going to have an asymptote here, and at negative pi over 2. And I know that graph looks something like this. And then comes down here. So that's secant. So as I approach pi over 2, I have some infinite behavior going on. So I'm going to write this here, and sorry, this is all blending together. So I know the top is infinity. Now if we look at 1 plus tangent of x, right, we know tangent is sine over cosine. So again, we see those asymptotes at pi over 2. And I'll have one at negative pi over 2. And now normally we would go through the origin, but since we have plus 1, this is shifted up. So I'm going to look something like this. Right, and then that's just going to repeat. So again, as I'm approaching pi over 2, I have infinite behavior. So now we know our form is infinity over infinity. That is an indeterminate form. So we know we can go ahead with L'Hopital's rule. So I'm going to jump down here. And now I'm looking at the limit as x approaches pi over 2 of secant x over 1 plus tangent of x. Okay, so we said we know that's an indeterminate form. So we're going to go ahead and apply L'Hopital's rule. So we're going to differentiate the numerator and the denominator. So in the numerator, we're going to get secant x tangent of x. On the bottom, we're going to get secant squared of x. Now, I'm going to simplify this a bit. I notice that I can cancel a secant out of the top and bottom, so this is gone, and this is no longer secant squared. So now I have the limit as x approaches pi over 2 of tangent of x over secant of x. Now, tangent, I know, is sine over cosine, and secant of x is 1 over cosine of x. So if I were to multiply the top and bottom by cosine of x, what this really simplifies to is the limit as x approaches pi over 2 of sine of x. And so now I can actually just plug this in. Sine of pi over 2 is 1, so my limit is 1. Now notice we actually only applied L'Hopital's rule once here when we differentiated. The rest was just simplifying or rewriting this using algebra so that we could do our limit. All right, so for our last example here, the limit as x approaches infinity of e to the 2x over 2x squared. So this again is going to give us infinity over infinity. So we go ahead with L'Hopital's rule. So we get limit as x approaches infinity of e to the 2x times 2 over 4x. There's not really anything I guess I could do a little bit to simplify. So this is the same as the limit as x approaches infinity of e to the 2x over 2x. I'm just factoring a 2 out of the top and bottom and canceling that. But I notice now if I go to try and plug back in, I still have infinity over infinity. And so L'Hopital's rule allows me now to just go again. So I'm going to take the limit as x approaches infinity, and I'm just going to differentiate again. So again, I'm going to get that e to the 2x times 2, but now I just have a 2 on the bottom. So if I cancel this out, I get the limit as x approaches infinity of e to the 2x. And now in this case, if I think of, we can't really plug it in, but if we think of x getting larger and larger, we know this quantity is going to go to infinity. So that's our limit. So this is the first example really where we did two applications of L'Hopital's rule. We differentiated once here, but when we tried to plug it in, we still had an indeterminate form. So then we differentiated again here, which allowed us to calculate that limit. So again, this just gets us around some limits that we haven't been able to calculate up until now. So from here on out, we're just going to be reviewing everything we've learned so far in this chapter. That's all for today.